All right, so here's our first example. We have a block coming in, B, with an initial velocity of 15 meters per second. It's going to hit the stationary block here and then compress the spring. You can see there's a nice little hook here. So we're going to assume that once these hit, that they'll stay connected. So considering that, we've got a spring constant of 10 kilonewtons per meter. We've got a mass of 15 kilograms, a VA of 0 meters per second, a mass B of 10 kilograms, a VB of 15 meters per second, and these two blocks are going to couple together after impact. So let's find our maximum compression of the spring. So this problem is actually kind of two problems in here. We're going to have two things that we're going to look at. First, we're going to look at what happens right after these impacts, and that's going to be a conservation of momentum problem. And then once these two couple together, then this becomes a conservation of energy problem, as that kinetic energy from this block coming in is going to be kind of transferred into potential energy stored in the spring. So there's kind of two steps of the problem. So let me write those two down. Here we go. We're going to write those two down. So first, we have conservation of momentum. And then we'll have conservation of energy after that. So let's look at those two pieces. So all right, so looking at our conservation of momentum problem, we're going to have something that looks like this. Remember that we're using L1 equals L2. Remember, these stand for linear momentum. So we can say at the beginning we have mass B moving. So that's our initial linear momentum for mass B. For mass A, thinking about this, mass A is not moving, so we are just going to go ahead and leave that out. That's going, mass A doesn't have a velocity. Velocity is 0. No value there. After these two collide, they're going to stick together, so we can put the two masses together. We can say mass A plus mass B, and we'll call this velocity final. This is going to be the velocity after impact. That's velocity after impact. So rearranging this a little bit, we'll say VF becomes mass B over velocity B over mass A plus mass B. Plugging in our values for each of those, we know that mass B, I'm really good at drawing these little lines here. Let me get rid of some of those, hold on. Mass B, we said, is 10 kilograms. Mass A is 15, so we'll put those two masses in here. These straight lines are great. I wish I could figure out why it keeps drawing these for me. All right. And then we'll put in our initial velocity, which is 15 meters per second. If we solve this, we'll get 6 meters per second. great, it just erased it. That's fantastic. So let me just rewrite that in here, sorry. I'll just leave myself some space. We'll say VF equals 10 kilograms times 15 meters per second divided by 10 kilograms plus and let me go ahead and all right. All right, so there we are at 6 meters per second. So that's our initial problem. We did the first one, which is conservation of momentum. Let's look at conservation of energy now. Now that we know the combined weight of the blocks together, let's switch colors for this. Let's go to a blue here. We'll call this conservation of energy. We know the conservation of energy looks like this. T1 and T2 are our kinetic energies. V1 and V2 are our potential. Thinking about these two cases, this is going to be just after impact. And this is going to be just after full compression of the spring. So putting these two together, we say, okay, well, our potential energy at the beginning, just after impact, this thing has no stored potential energy, so V goes to 0. And after full compression, our kinetic energy goes to 0. So we know that T1 is equal to our V2. We plug in what we know. This is going to be 1/2 mass times velocity squared. This will be 1/2 K times S squared. I don't know why it's drawing all these fun little lines, but it's great. Now, looking at this, I can simplify this a little bit. The 1/2s drop out. If I want to solve for S, this looks like S equals the square root of the square root of, it's going to be mass times velocity squared divided by K. And if we plug in those values, mass, we said is going to be the mass of the whole object. So it blocks A and B together. Our velocity, we said, was 6 meters per second squared. And we're going to divide that by K. Now, K in this case, we got to be careful because in this particular value, we have a K of 10 kilonewtons per meter. You look here, we got 10 kilonewtons per meter. If we plug that in here, we need to make sure that we write the right units. So I'm going to go ahead and write this in terms of Newton meters. And if we plug that into our calculator, we will get 25 times 36 divided by 10,000. That gives me a compression of that spring 0.3 meters, excuse me, meter seconds. What am I doing here? Let's change that to meters. All right.